Hello, my name is Brian Boots, and today I'd like to talk about some innovations in HFSS to push boundaries of chip scale extraction. And I'd also like to introduce two new workflows, RaptorH and ECADExplorer. Let's start by taking a quick look back in time at the history of HFSS, and specifically the history for on-chip extraction. It all started 3 decades ago with this coax to waveguide transition with HFSS version 1. And I'd like to start the journey by just having you focus on this initial model, the first ever solved, which amounted to 10,000 unknowns and a solve time for a single frequency point in excess of 10 hours. It was an entire decade till we started seeing on-chip extraction emerge, and it really came about as a result of a need for better characterization of high quality factor inductors. So it was really emphasizing single device extraction for simple inductors with high accuracy requirements. This model is 300 microns on side, so less than 1/10 of a square millimeter, and it was solved in around 700,000 unknowns. It was about a decade and a half that this continued, and over the course of this decade, HFSS really solidified itself as the gold standard for device level extraction on chip. In terms of technology innovations, it was really focused on methodology, with some emphasis on automation in the form of macros and scripting. We saw progress in the form of mesh seeding and improved boundary conditions to better characterize skin effect. And we saw stabilization of the matrix solvers for electrically small devices and improved accuracy for low frequency extraction. Around 2014, we introduced two innovations. One, the user-facing workflow for layered devices. And this was principally used for package and PCB extraction, but also very relevant for on-chip device characterization. It gave you a layout-based workflow to access the same three-dimensional finite element solver that we previously had asked users to operate in a 3D CAD environment for. Shortly after, we also introduced AutoHPC. And AutoHPC conceptually took the chore of asking a user to allocate optimally complex compute environments for a specific solve process. So AutoHPC takes the software and has the software configure itself to better leverage multiple nodes and large memory footprints for the fastest solve possible. Around 2017, we introduced the phi mesher and the distributed matrix solver, and these are the two linchpin technologies that really enabled the hockey stick growth in capacity and addressable space in this area. But it wasn't until a little while later that we realized that. And that's because while the phi mesher was tuned for layer-based structures, it wasn't doing a good job dealing with the complexities of on-chip geometries. And while the distributed matrix solver was great and did a wonderful job spanning across multiple nodes, it really required a reduction in memory footprint and improvements in efficiencies across the entire solve process to reach the capacity needed for block level extraction using HFSS. And so it was only around 18 months ago where we brought all this together and we could start to realize solves on the order of 10 million unknowns. And from point of perspective, 10 million unknowns will get you the top 5 or 6 metal layers in a 2 square millimeter extraction in a common an advanced process. So now we're talking about an order of magnitude advancement over the course of around 19 years. So moving from device level 1 million unknowns to maybe block level at 10 million unknowns. But in the last 3 to 6 months, we've gone another order of magnitude. And this has really come about by revisiting some of the things that are happening in low level of the fee mesher, introducing what we call an IC mode for the fee mesher. And we'll talk more about this in subsequent slides. And then further enhancements and progress with the distributed solver and the making that available in a cloud infrastructure has really forced a lot of revisiting of some basic performance bottlenecks. So between all of this, we've pushed the boundary to in excess of 100 million unknowns, which again gets you an additional order of magnitude and maybe 30 square millimeters for the top 5 or 6 metal layers. So there's been this very steady progression and then rapid acceleration in capabilities only within the last 12 to 18 months, I would say. So why? Why are we focusing all this R&D energy and effort for workflows at chip scale? A few things are happening that we see in the market. One is increasing demand due to 5G RFIC development, where we're seeing increased complexity and density of radio circuits and layouts with advanced node processes. We're also seeing an emerging desire to bring full wave extraction to other areas, traditional signal integrity areas, but on chip in the form of silicon interposers and high bandwidth memories. And then finally, a desire to better understand the interaction between chip and package and better characterize the system level effects on the chip performance. A lot of this is also being driven by packaging technologies. So as people have moved more to 3D packaging, be it stacked dies, broader use of redistribution layers, wafer level packaging, and so forth, we get more density in three-dimensional space. And this requires often three-dimensional aware solver. We're also seeing an emergence in 3D ICs and TSVs. And all of this combined is just creating a more complex electromagnetic environment where we need to better understand complex coupling mechanisms, be them block to block, chip to package, block to seal ring, and this emerging concept of RF integrity. So bringing a lot of what we've generally referred to as signal integrity workflows and concepts and pushing them onto the chip and better understanding these coupling mechanisms. And to do that, we've turned to HFSS, our gold standard finite element solver. But it's not just enough that we provide breakthrough technology advancement for meshing and solve to push capacity levels. We also need to make that technology accessible. And so at the end of March, we introduced a new workflow called RaptorH, which provides streamlined access to not just HFSS, but a hybrid peak random walk solver that's specifically tuned for on-chip structures. And it brings that in a streamlined environment specifically for silicon designers with support for encrypted technologies and tight integration with third-party platforms. We've continued to invest in our traditional workflows as well because these provide a unique experience and access to advanced features and post-processing for our more traditional HFSS user base and also those interested in system-level integration. And we've done that with the introduction of the ECADExplorer workflow. And we'll talk more about both of these workflows in the next few slides. So when we talk about a unified chip-to-system workflow and toolchain, it really comes on the heels of an acquisition that Ansys made just over 12 months ago and the integration of HFSS into that platform. And that's what we're calling RaptorH. So RaptorH spans in the Helix Central platform from floor planning all the way up to block-to-block coupling and even perhaps that first layer of package to die interaction. It provides some unique features with robust technology file handling and perhaps more importantly, encrypted technology handling, but also consideration for layout dependent effects in advanced processes and access to the peak solver of RaptorX. This flow is very tightly integrated with third-party platforms, and it's really focused on extraction and back annotation into those workflows. So it's really focusing on a silicon designer workflow. But it transitions seamlessly into our existing workflows in the form of electronics desktop. So if someone needs to access more advanced features or exert more flexible port configurations or simulation setup parameters, they can easily move from RaptorH into electronics desktop and leverage those capabilities. So RaptorH, it really is a streamlined workflow for HFSS. And you see virtually all of the user interface on this single slide. So it's 4 panels. It's asking the user to basically choose adaptive frequency and extraction range and configure a few additional parameters for the extraction. But it's taking a lot of the complexity out of the geometry manipulation and port setup and so forth. So it is a new product, and it does integrate 2 world-class solvers under a common interface. It provides support for encrypted technologies and some advanced layout processing capabilities, particularly around layout-dependent effects and process corners and temperature planning. It is specifically focused on tight integration with third-party platforms, Cadence Virtuoso, Synopsys Custom Compiler, and the ability to perform that S parameter extraction and back annotate that model into those environments. Now, from a designer perspective, there is real power in having access to 2 world-class solvers from one streamlined interface. And my view on this is one of confidence. So if we can get 2 disparate methods to achieve a tight level of correlation, I think it lends confidence to the simulation methodology. And so here we see for a transformer coil, the ability to achieve peak Q correlation of less than 3% and an inductance correlation of less than 1%. And if you've done this simulation game long enough, you know that doing this with 2 completely different methodologies can be difficult, but the ability to do it from a common interface is a very powerful proposition. On the right, you'll see a table of a few additional test cases, and I want to stress that this workflow provides the capability to access those same technology breakthroughs that are available in our traditional workflows. So you'll see complexity spanning from 50,000 TETs, which may be a single device, all the way to a couple million to tens of millions of TETs, which would be more on the order of a block level extraction. So we've talked about RaptorH, which is really focused on silicon designers and this streamlined usability. But we've also added additional capabilities for this application area within our traditional workflows. We've introduced a new purpose-built tool called ECADExplorer, and we've made the investment in mesh technologies to accelerate usage and complexity. And best of all, these workflows are complementary. So we can easily transition between RaptorH into electronics desktop by virtue of the electronics database. And the electronics database is a centralized data management repository for ECAD geometries and setups. And it's accessible by a variety of tools across the Ansys ecosystem. So it allows interoperability within the Ansys ecosystem, and it allows us to take models from RaptorH and move into electronics desktop. So how do we use ECADExplorer, and what is it? Well, ECADExplorer is a purpose-built user-driven application whose sole purpose is for healing and doing the geometry simplifications necessary at IC scale to leverage the HFSS solver. So we've really focused on high performance geometry operations specific to on-chip structures. And when operating at that scale, containment and violation checking, having those check-ins built into the geometry operations is critical. So we do integrate those sort of design level checks with the geometry processing. We're also providing more capacity and visualization capability that are required for GDS type files. It's a very hierarchical environment, but ultimately it's an intermediate between the GDS file and the XML technology description and our traditional workflow of HFSS 3D layout. So let's walk through an example and discuss what this looks like. So as of 2020 R2, we've integrated a lot of the pre-processing directly into the XML technology description. And this brings a level of repeatability because we know you're not just going to be generating one version of this model. And so once you characterize your technology and your pre-processing has been codified, you can actually capture that in an XML, and then you can use that repeatedly with additional revs of the GDS file or different cutouts or different blocks. Once we do that translation, we end up in Electronics Desktop with a HFSS 3D layout design, and everything from that point forward is the familiar workflow. So we can configure ports, we can insert an HFSS setup, and then importantly, we choose the new IC mode in that setup. And then we just solve. And all of this can be automated. There's a rich scripting API. The EDB itself has a very comprehensive API. So this can be as hands-off or hands-on as needed. At the end of the day, we have a model and we need to solve in HFSS. And for this example, it's a very modest example. I think when you look at it at first, you might think it beyond the scope of what we've traditionally solved with HFSS. But with these breakthroughs in technology, it's actually less than 1 hour of total simulation time with an initial mesh on the order of 10 minutes and 780,000 TETs. And a total matrix size of 5.3 million TETs. In terms of memory footprint, it took 6 gigabytes of RAM across 8 nodes, so a total of 48 gigabytes of distributed RAM, leveraging the distributed matrix solver. So now let's look at some system level effects. For this exercise, we mocked up a representative package substrate, and we generated 2 cases. Case A has an open top metal layer, so it's really something closer to a cavity type placement. Case B, the top metal layer has been flooded with ground metallization. And then on the back side of the package, we just have a circuit element providing some decoupling capacitance between power and ground. I want to highlight 2 features here. One is this ability to integrate complex decoupling capacitor models into the system matrix with HFSS. And this eliminates the need to actually create ports or right-hand sides. So we can directly integrate these capacitor models either on the board or in the package, or on the chip for that matter. Further, once we have the extracted models, we can put it in a circuit environment, and we can actually run a system level simulation. From that system level simulation and that real world excitation, we can calculate the vectors and push those source vectors back into HFSS for fields post processing. We call this push excitations. It's a very powerful feature when you're trying to understand specific coupling mechanisms in a, say, transient environment or a complex RF excitation. for this particular example, the insertion loss deviation in the two cases is a little underwhelming. So, but there's power in understanding this too. So what you see here is insertion loss from the single-ended transmission line on the first stage to the positive and negative points on the other side of the transformer. And you'll see that there's not a lot of change on the insertion loss, be it with the flooded ground plane or the open ground plane. However, if we probe the power plane and we look at the input impedance, we do see between 5 and 6 gigahertz, 30 to 40% variation, even if it's just a couple tenths of ohms. We see that the input impedance is varying considerably over that frequency range for the two cases. So perhaps there are some design changes or some design considerations that you can make because at high current draw, perhaps that shows up as too much fluctuation on the power plane. So how did we get here? There's really been a couple major advancements in the workflow to address on-chip modeling and push boundaries. One, first and foremost, is this new IC mode in the HFSS simulation setup option. And this really, at a low level, it improves handling for high aspect ratio geometries, automates some misalignment and some healing operations, and does those two things with an eye towards improving overall mesh quality and general first pass robustness for mesh success. All of that together actually accelerates adaptive refinement and can result in better performing simulations in aggregate. A lot of this was also facilitated by new and improved geometric processing in the context of ECADExplorer, and more recently during translation itself, where we formalized the via layer type, which provides more intuitive mapping between IC technologies and an HFSS setup, but it also provides context wherein you can provide directives for this automation and consolidation of vias, for example. It also provides a less error-prone workflow and something that can be repeated over and over in an automated fashion across an organization. And finally, we improved net tracing performance during the GDS translation process. So here we see two cases at rather extreme scale, and I just want to highlight a few things. This was facilitated by this IC solver mode. So the things we're doing in mesh really allowed us to get access to the solver technology, which was capable of addressing problems of this size. But perhaps from an engineering perspective, most importantly, it took the setup time from almost a week to less than a day. So I think from an engineering perspective, that's considerable. And if we look at what this means, we're generating case A, 20 million tets with 80 ports, a converged matrix size of 40 million unknowns on a distributed cluster environment with 2 terabytes. We can solve that now in 30 hours. And case B, 40 million tets, so 2x initial mesh size, 10 fewer right-hand sides, converged mesh of 70 million unknowns, required 3 terabytes of distributed RAM, and we're solving that in less than 2 days, well less than 2 days at 40 hours. From a scaling perspective, I really like this slide because it demonstrates that over an order of magnitude of complexity. So here we're plotting initial mesh size on the x-axis and the time to generate that initial mesh on the y-axis. And we're seeing over these 5 cases of an order of magnitude span from 3 million tets, which was completely unaddressable in this domain as recent as 12 months ago, to 40 million tets for case D, which only in the last couple of months have we actually been able to mesh and solve. We're seeing linear growth in the time required to produce that initial mesh, which includes all the pre-processing. And that's pretty impressive from a software and R&D perspective. All right, so wrapping this up, we've reviewed some major breakthroughs in technology that are pushing HFSS into uncharted territory. And it's really allowing us to bring full wave gold standard extraction technology to a completely new domain. It's improving our ability to capture and understand complex coupling mechanisms, be them stage-to-stage coupling, block-to-block, block-to-seal ring, and then those system-level effects, chip-to-package, chip-to-package-to-board. And a lot of this has been facilitated by breakthroughs in mesh technology and by advances in our distributed direct matrix solver and HPC technologies. And it's to the point now where with 2020 R2, we're seeing initial meshes in excess of 20 million tets becoming somewhat routine. And if we think back to that first slide I presented, the idea of meshing 20 million tets or a single block or multiple blocks using HFSS gold standard solver technology with no compromises is mind-boggling, and it's very exciting. And more than that, as an engineer, I think it's very instructive to not just get this black box of S parameters and to see a problem, but then to be able to actually visualizing that problem in the physics. So not only can we solve these, we can plot the electric fields on the chip, and you can do a better job root causing the source of that block to seal ring or that inductor to seal ring coupling. And there's real power in that from a simulation perspective. And with that, I'd like to thank you for your time.